Welcome to today's explainer on DSA math concepts. If you've ever hit submit on your code only to get slapped with a dreaded time limit exceeded error, you know exactly why we're here today. We are going to completely upgrade your algorithmic toolkit from naive brute force coding to highly optimized mathematical logic, transforming the way you approach numbers in your code. Here is what we're tackling today: primes and the sieve, playing around with digits, Euclid's GCD and LCM, and finally, mastering modular arithmetic. Let's get right into it. Section 1, Primes and the sieve. Let's look at how we count primes. So imagine you need to find how many prime numbers exist up to a certain number, n. The absolute brute force way: just run a loop and check every single number for divisibility. But if n is huge, you are literally guaranteed to get a time limit exceeded error on platforms like LeetCode. To get around this, we use a brilliant method called the sieve of Eratosthenes, which entirely flips the script. Think of this algorithm exactly like a giant strainer, or a chalani. You start out super optimistic, assuming every number from 2 to n is a prime. You begin at 2, which is prime, right? But then you act like that strainer, filtering out all of its multiples. So 4, 6, 8, they all get tossed out as non-prime. Then you just move to the next valid number, which is 3, and strain out its multiples. You keep doing this, systematically deleting multiples at every single level. By the end, the only numbers left sitting in your strainer are your pure primes. It's incredibly powerful and fast. Moving right along to section 2, playing with digits. Time to extract some base 10 numbers. Now, whether you need to sum the digits of a number, count them, or print them, the foundational logic is exactly the same. We use the classic base 10 duo. By repeating 2 simple operations, we can extract any number's digits in O of log n time. Since we're working in base 10, taking a number modulo 10 grabs its last digit as a remainder. Then, you simply divide that original number by 10, which literally chops that last digit off. Throw this inside a loop until the number hits 0, and you're golden. The time complexity is log n base 10, because you're repeatedly slicing the number down by a factor of 10. This exact logic is perfect for Armstrong numbers. You can easily check for one by extracting those digits and summing their cubes. Take 153, for example. Using our base 10 duo, we pull out the 3, then the 5, then the 1. We cube them to get 27, 125, and 1. Add those up, boom, exactly 153. If the sum of the cubed digits matches the original number, you've got yourself an Armstrong number. We use a very similar digit extraction trick for palindromes. To check if a number is a palindrome, you just check if it equals its reverse. But hey, quick edge case to remember. Immediately return false for negative numbers. A negative sign at the front means there is no way it's going to read the same backward. Just an easy trap to avoid. Let's trace how we actually write the code to create that reversed number, digit by digit. We start with a reversed member variable set to 0. First, we extract the last digit of the original number. Then, we multiply our reversed number by 10, which shifts everything over a place, and add the extracted digit. Finally, divide the original number by 10 to chop off the used digit. Just repeat that until the original number is 0, and you've successfully built the reversed version. But watch out, because this is where the overflow trap gets you. Reversing a number can easily push it out of the standard 32-bit integer range. The second we multiply our reverse number by 10, we risk exceeding the max integer limit and crashing the whole thing. So right before you do that multiplication step, you absolutely must check if your current reverse number is already greater than int_max divided by 10. If it is, return 0 immediately, because going any further is going to break your code. All right, on to section 3, Euclid's GCD and LCM. Let's talk about efficient divisors. When an interviewer asks you to find the greatest common divisor, searching for factors one by one is going to be way too slow. The brute force method tests every single number from 1 up to the minimum of the 2 numbers. Enter Euclid's algorithm, the hero we need to slash our time complexity. Euclid realized something mathematically brilliant. The GCD of 2 numbers, a and b, is exactly the same as the GCD of the difference between them and the smaller number. If we trace Euclid's repeated subtraction for the numbers 28 and 20, you just keep replacing the larger number with the difference. Eventually, we hit 0, leaving us with a GCD of 4. It works beautifully. But, if one number is significantly larger than the other, you're going to be subtracting for a really long time. We can actually do one better. Since repeated subtraction is really just division, we can swap out subtraction for a modulo operation to hyper-optimize this calculation. Instead of continuously subtracting 8 from 28 until we get below 8, we literally just take 28 modulo 20. That immediately jumps us down to the remainder, vastly reducing the number of iterations you need to reach 0. The moment one of the numbers hits 0, the other number is your GCD. Simple as that. And the best part? Once you finally have that GCD, finding the least common multiple is just a super fast one-line formula. You multiply your two original numbers together and divide by their GCD. That is literally the whole shebang. No complex loops needed for the LCM once you have Euclid's algorithm in your toolkit. Finally, Section 4, Mastering Modular Arithmetic and Preventing Overflows. We've reached the ultimate boss of competitive programming, one that trips up so many beginners. If you've ever practiced DSA, you have definitely been intimidated by this massive, very specific number, 10 to the 9th power plus 7. Often, a problem will ask you to calculate something absolutely huge, like a permutation resulting in 50 factorial. That value is so large it's never going to fit inside standard integer types, so the prompt casually tells you, hey, just return the answer modulo 10 to the 9th plus 7. But why that number? Well, we use it because it prevents your variables from overflowing during heavy calculations while still keeping your answers perfectly verifiable. Since 10 to the 9th plus 7 is a very large prime number, taking the modulo limits the maximum size of your output, but it also preserves a huge range of unique possible values. Basically, it allows the automated grader to verify your logic is actually correct without completely blowing up your computer's memory. Think of these rules as your essential modular arithmetic cheat sheet. Modulo perfectly distributes across addition, subtraction, and multiplication. If you're building a massive number inside a loop, you do not wait until the very end to apply the modulo. You can safely apply it at each individual step of your addition or multiplication. This guarantees that at absolutely no point in your loop does the temporary value ever exceed the integer limit. Just, be super careful with division because that follows totally different rules. You now have a seriously solid math toolkit for your coding interviews. But to truly master dynamic programming, you're going to need to explore power exponentiation and Catalan numbers in your next practice session. Today, we leveled up from naive brute force to elegant mathematics, but recognizing classic Catalan parents or calculating x to the power of n efficiently is what separates good programmers from the truly great ones. So, how will you apply these optimized patterns in your next coding challenge? Thanks for joining me on this explainer, and keep coding.